Today we're going to be getting familiar with the instantaneous rate of change for a function. In the previous video we learned what the average rate of change is. The average rate of change is the slope of the secant line that passes through 2 points of our interval. For starters, we're going to be working on an example of a line. F of x is equal to x plus 2. Within this function we know the y-intercept to be 0, 2, and when x is equal to 1, 1, 3, which will be right here. With 2 points, we can find the line graph to look something like this. This will be our line equation for f of x. Now, with this, how do we find the average rate of change? The average rate of change between the intervals of point A and B, which I need to mention, points between point A and B inclusive, point A, point B, will be equal to the slope of the secant line that passes through these 2 points. And the slope of the secant line between points A and B will simply be the change in y divided by the change in x relative to these 2 points. We know the coordinate of A to be equal to 0, 2, the coordinate of B to be equal to 1, 3. Therefore, the slope of the line that passes through A and B will be equal to 3 minus 2 divided by 1 minus 0. Which will be equal to 1 divided by 1, which is equal to 1. Therefore, the average rate of change for the intervals of A and B will be equal to 1. And notice how 1 is equal to the slope of f of x. The slope of f of x will be equal to 1 as well. The reason for this is because the interval between points of A and B will both lie within the function of f of x. Those two are points of f of x after all. So the average rate of change for any given interval within the line will be equal to the slope of that line. But now let us try to find the instantaneous rate of change. The instantaneous rate of change for point A. How do we find the instantaneous rate of change for point A? Well, let us apply our knowledge of the secant line slope, which is the average rate of change, to the instantaneous rate of change. The instantaneous rate of change will be defined by the following: the slope of the tangent line relative to point A. And point A will just be the point for which we wish to find the instantaneous rate of change of. So with this definition in mind, how are we supposed to find the slope of the instantaneous rate of change of A if we're only given one point, which is point A? Well, let us use our knowledge of the average rate of change to assist us. The change in y for this will be this vertical line right here. And the horizontal line this red color, will be the change in x. So that right there will be the change in x, represented by delta x, and this segment right here will be delta y, representing the change in y. So with our knowledge of the limit, if this limit of the function of x plus delta x minus f of x divided by delta x when delta x infinitely approaches 0 should give us the instantaneous rate of change of A. And you might be wondering, how did I derive this? Well, how I derived this is by using our definition of how to find the slope of a line. The numerator right here, which is f of x plus delta x minus f of x plus delta x will simply be point B's y value. Because remember, the little red segment right here represents the change in x from A to B. So when f is parentheses x plus delta x will give us the point of B's y coordinate. Subtracted by f of x, well, f of x when delta x approaches 0, so f of x will simply be our point of A, divided by delta x, which is our change in x. Because when our change in x between points A and B gets infinitely small, it will become the slope of the tangent line of point A. So we can apply this knowledge into our function to be equal to the limit when delta x approaches 0 of f of x plus delta x, which will be x plus delta x plus 2, because f of x plus delta x will be our input value. X plus delta x is substituted into the x variable within x plus 2 to get x plus delta x plus 2 minus the function of x, which is x plus 2, divided by delta x. This can be further expanded to be equal to the limit when delta x approaches 0 of, if we expand it, x plus delta x plus 2 minus x minus 2 divided by delta x. We can cancel out the x and x right here to be equal to the limit when delta x approaches 0, and canceling out the positive 2 and negative 2, delta x over delta x. A delta x divided by delta x will be equal to the limit when delta x approaches 0 of 1, which will be equal to, remember, the limit of a constant is equal to that constant is equal to 1. Notice how that this discovery of the instantaneous rate of change for point A will be 1 is the same thing as the slope of f of x. So what can we conclude here? We can conclude that the instantaneous rate of change, the average rate of change for a line function such as x plus 2 will be equal to, both of them, the slope of that line. And with this knowledge in mind, we can move on to a harder example, which is a more general example, where we analyze the instantaneous rate of change for any function, whether that be a conic, a curve, or a line. So let us say we have this function f of x, and I want to find the instantaneous rate of change for this point of A. Well, to help us with this, let us find another point, a point B, because we can take the limit of when B infinitely approaches A to get our instantaneous rate of change. We use our previously understood knowledge to assist us in proving our new knowledge. So point A, let's say has the x coordinate of x0, y0, or rather x0, f of x0. Because this black squiggly line, this black curve, is simply f of x. So when the value of x for point A right here, this will be x of 0. And when we apply x of 0 into our function, draw a vertical line over, this point will be f of x0, which I could draw better. This point will simply be f of x0 because we substitute x0 into our input. And we also know that the point B, if I let point B be equal to x1, f of x1, then the x value, it will look like something like this. If I draw a vertical line down, this point will be x of 1. This horizontal line to the y-axis will be f of x1. Hence, we have the definitions of coordinate points in play for this curve. And I want to find the instantaneous rate of change for point A. How do I find it? Well, I take the limit of the slope of the secant line of points AB. Well, the secant line between points A and B will look something like this. And the slope of this red line will be our average rate of change between the intervals of points A and B. So if I take the limit if I define this change right here, this distance, to be delta x, the change in x, and if I define this distance between the points of f of 1, or f of x of 1 rather, to the f of x0 to be delta y, which is representing the change of y, then the limit of when delta x, or when delta x infinitely approaches 0. And why do I want to infinitely approach 0? Because when this delta x gets smaller and smaller, so when delta x gets even closer and closer to 0, so when the change in x gets infinitely minutely small, of the f of x plus delta x minus f of x divided by delta x will give us the slope of this instantaneous rate of change for a. This instantaneous rate of change is also known as the derivative. Derivative. D-E-R-I-V, or derivative. The definition of derivative will be the limit when delta x approaches 0 of the function of x plus delta x minus f of x divided by delta x. This will be our definition of the derivative in terms of a limit. Hence, we have understood what the instantaneous rate of change is. It is the derivative. And another way to write a derivative, in the less general format, this can also be equal to, given the graph to the left, will be equal to the limit when b approaches a of f of b minus f of a divided by b minus a. And these two limits are the same thing. The reason why for this is f of b minus f of a is simply our change in y, while b minus a will be our change in x. B is our x-coordinate of point B, a will be the x-coordinate of point A, f of b and f of a being the y value for those 2 points respectively. So this still correlates with our previous understanding of the average rate of change. The average rate of change and the instantaneous rate of change are just both slopes of a line. The slopes of a line, while the average rate of change being the secant line, the instantaneous rate of change being the tangent line. So here we have understood what the derivative is. In other words, the instantaneous rate of change. It is just the slope of the tangent line. In other words, to find that slope, the same thing how we would find the slope of any other line, the change in y divided by the change in x. Therefore, we have proved the definition of the derivative as a limit and understood what the instantaneous rate of change is.